In this video, I'm going to go over how to name simple ionic compounds, or binary ionic compounds, people call them. For those, we're just going to be doing main group elements. So we'll be looking at our two towers here and here. We're not going to worry about the transition metals. Those will be in a different video. And we're not going to worry about polyatomic ions. So I'm going to start by talking about Lewis structures of ions. So we've already done Lewis structures of atoms at this point, which is just writing the symbol of the atom and putting the valence electrons around the atom. That's going to be what you do first. And then you are going to add or subtract electrons to form the ion based on the charge. So if we go to our periodic table, I'm going to give you the charges of the main group elements. For group 1, so group 1 is this group right here. They will get a 1 plus charge. You might remember from when we first started the periodic table that most metals will all get a positive charge, and most nonmetals get a negative charge. Hydrogen, although you know it is a nonmetal, it also gets a positive charge. Group 2 gets a 2 plus charge. Group 3 gets a 3 plus charge. Group 4 we're going to skip over for now. Group 4A, Group 3A gets a 3 plus charge. Group 4A we're going to skip over for now. Group 5A gets a 3 minus. Group 6A gets 2 minus. And Group 7A gets 1 minus. Group 8A doesn't bond except in very specific circumstances, only the atoms at the bottom. We might encounter some of those later on in the course, but you do not need to worry about those in terms of naming them. So once you have added or subtracted electrons to form the ion based on the charge, you're going to write brackets around the symbol. Brackets in chemistry usually mean either concentration, which is something we won't cover right now, or that you've changed something. So we're using them here to indicate that we have added or subtracted electrons. And then we're going to write the charge on the outside of the bracket. So I'm going to show you a couple of them now. We're going to start with potassium. The first step is to write the regular Lewis structure of the atom potassium, which you know just has one valence electron because it's in group 1A. If you look at the charges that we just gave you, potassium also gets a 1 plus charge. And here's why I wanted to start with these Lewis structures. What's difficult or challenging about chemistry when you first start doing this is that electrons are negative and they also do a lot of the work in chemistry. So when you see a positive charge, it actually means you're going to remove that many electrons. So when you see a positive charge, you're actually going to remove 1 electron. We don't really write ones very often in chemistry, except in very specific circumstances that I'll talk about throughout the year. So if you just see a plus with no number next to it, it's a 1 plus. If you just see a minus with no number next to it, it's a 1 minus. So this says to remove 1 electron. So when I go here, I'll draw it without the dots. And then I put the brackets. And I just copy the charge to the outside of the brackets. So let's do tellurium. Tellurium is right here. It's in group 6A, so it has 6 valence electrons. And this 2- charge tells us that we're going to add 2 electrons. Then you put the brackets and the charge. So the only difficult thing here is that you are adding when you see negative and removing when you see plus. So the reason I want to do a couple practice of this is just to get you used to that. So if you want to pause this video and try these, then come back when you have them done. So for Br, we started with 7. And we added 1. For N, we start with 5. And we're going to add 3 because of that 3 minus. For SR, we start with 2, and it's 2 plus, so we're going to remove the 2. And then CS, we start with 1, and it's 1 plus, so we're going to remove the 1. And you might start to notice a pattern here, and that all the nonmetals end up with 8 dots around them, and all the metals end up with no dots around them. And that is so that they can follow that octet rule that we talked about when we did bonding. Okay? And that's true. Metals will all have 8 because remember they go out and seek out electrons to fill up their outer shell. Metals will end up with no dots because remember they gave away their outer shell electrons so that we just erased that outer shell and their next one became the full shell. And hydrogen, of course, is the exception to that. Okay. Before we do the crisscross method, let's go back up here and talk about if we wanted to bond aluminum and chlorine. Aluminum is a metal, and it has 3 valence electrons. Chlorine is a nonmetal, and it has 7 valence electrons. We know from our bonding conversation that these will bond ionically, meaning that the electrons will transfer from aluminum to chlorine, and that in order for chlorine to be stable, it needs to have a full outer shell of 8. In order for aluminum to be stable, it needs to get rid of all 3 of these so that it can go down to the next level and have a full outer shell of 8. So we can put this electron here in this empty space. But aluminum is still not stable. So in order to get rid of all of the aluminum's valence electrons, which we have to do, we're going to need 3 chlorines. Because chlorine only has 1 open space. So in order to bond aluminum and chlorine, you need 3 chlorines for every 1 aluminum. The way we write that in a chemical formula is aluminum has a 1, 1 aluminum, 3 chlorines, but as I mentioned a little bit earlier, we don't really write ones in chemistry, so it will just be AlCl3. And the subscripts, these little numbers on the bottom, tell you how much of each atom you would have in that compound. So for aluminum chloride, you would have 1 aluminum and 3 chlorines. Now, you could do this every time, but sometimes it might get really complicated. Like, for example, if we're doing Ca and P, Ca has 2 valence electrons, phosphorus has 3 open spaces, right, because it has 5 valence electrons. So it's going to be a little more difficult to figure out how many of each you need. So that's where the crisscross method comes in. The crisscross method is not actually science, it's just a trick that helps us get to the science faster, so it's easier to handle. So what you will do for the crisscross method is write the 2 element symbols with their charges. You just look them up on the periodic table. Then you move the charge to the subscript of the element. When you do that, you get rid of the plus or minus. That's very important. When you make them a subscript, the numbers lose their plus or minus. You don't want to have a plus or minus as a subscript. And then reduce or simplify the subscripts if possible. So let's do some examples. Okay, let's go to aluminum chloride. We now already know that that formula is AlCl3. Let's see how that works with the crisscross method. Al on our periodic table has a charge of 3 plus. Al, 3 plus. Cl gets 1 minus. That's its charge. The next thing we do is move the charge to the subscript of the other element and get rid of the plus or minus. So the 3 goes to the subscript, bottom number of Cl. The 1 goes to the subscript, bottom number of Al. And then you would get Al1, Cl3. We don't write ones in chem most of the time, so again, we would get AlCl3. That's what we got last time, but we didn't have to do all the Lewis structures and figure out how many we needed. So now let's figure out that calcium phosphide, which we had talked about would be a little bit harder. So we look up calcium and phosphorus. Calcium has a 2 plus charge. Phosphorus has a 3 minus charge. Calcium, 2 plus. Phosphorus, 3 minus. We crisscross them. So we get Ca3P2. Remember to get rid of the plus or minus. That is the formula. And if you wanted to test it out, you could write 3 calciums with their 2 valence electrons each, 2 phosphoruses with their 5 valence electrons each, and you will have a place for each calcium valence electron to fit onto a phosphorus. For our next one, let's do magnesium sulfide. Magnesium is here. It's a 2 plus charge. Sulfur is here. It's a 2 minus charge. When you crisscross them, you get Mg2S2. That brings us to our third thing. Reduce or simplify the subscripts if you can. So these right here can be simplified. You want to think of them, you look for the lowest common factor, whatever you want to think of it as. You can think of them as a fraction because they are a ratio, whatever you want to think of them as. But see how we can divide both of these by 2, and then they would be 1. We don't write ones, so your final answer would be MgS for magnesium sulfide. A lot of students ask me, do we have to simplify? You do. For ionic compounds, you have to simplify or it will be incorrect. So if you want to pause the video and give these a shot, and then come back and I will have the answers done for you. So that's writing formulas for simple or binary ionic compounds. Now let's talk about going the opposite way. When you're given a formula, writing the name. You might have noticed that I've been using all of these different words to mean elements. Like instead of phosphorus, I've been saying phosphide, or instead of oxygen, I've been saying oxide. And that's just the way the language is in chemistry. So when you're going formula to name, it's pretty easy. You just write the name of the first word, which is metal in ionic compounds. Then you write the name of the second word, which is the nonmetal, but replace the ending with IDE. It takes a little while to get used to what some of these IDE endings are, but remember, we only have a handful of metals, of nonmetals that bond because the noble gases aren't going to bond. So you get used to them pretty quickly. If you need some help or guidance as you're getting used to them, just ask me for what the IDE ending is of an element and I will give it to you. So here we have barium and nitrogen. So we would just write barium, nitride. You don't have to put anything about the numbers not for simple binary. And so that's your answer. Nitrogen becomes nitride. Then we have potassium, sulfide. And here we have gallium oxide. So pause the video real quick and do these three. I know this is pretty easy, but I just wanted you to do a few of these just to get those IDE endings into your notes so that when we're practicing in class, you have them ready. And there you go. So that's it for naming simple ionic binary compounds.